and I would like to invite Hans Gleisner as our next speaker. And he will talk about ROMSAF climate data records, plans and applications.
Okay, so good morning. My name is Hans Gleisner. I work at DMI in Copenhagen. So these guys here is the ROMSAF team at DMI. So I will talk about our climate data records, and also I will mention a few of the applications where we have been involved in, and I will also say something about the development plans. So this is the existing data record. It consists of CHAMP, GRACE, COSMIC, and METOP.
I'm sorry, if you could speak a little closer to the podium.
Okay.
Thank you.
So it's CHAMP, GRACE, COSMIC, and METOP. It was reprocessed, well, it's 5 years ago now. So it was released in 2019, consisting of 15 years of data. We also, at the time, we also started to generate an interim climate data record based on METOP data. So it's released monthly, and it's now up to more than 7 years of data. So the combined CDR and ICDR time series, it covers, well, it's more than 22 full years now. But as you can see, as we heard here, there are many more data available now, and since 2017, we only have METOP data available in this data record. So the climate data records consist of, well, when we talk about CDR, we mentioned both the set of profiles and the set of monthly mean gridded data. The variables are the standard variables: bending angle, reflectivity, dry variables, temperature, pressure, and geopotential heights on dry pressure levels. We also have a set of 1D variables, temperature and humidity. We also generate tropopause heights, both as individual data points and as gridded monthly mean data. So we have actually, well, the formal products, we have 6 different definitions of tropopause height, which we can compare, even though it's only one of them who is the actual formal product, ROMSAF or HUMASAT product. We also deliver, well, pressure profiles and surface pressure also, but those two are not generated into monthly mean data. All right, so we have these 4 missions, and of course we want to use them combined, put them together to a multi-mission data record to be used for, well, trend calculations and these kind of things. And we know that it's an underlying assumption that we can sort of combine data without doing any intercalibration between missions or between instruments, as they do in the IR or microwave world. But so here we have computed. This is for bending angle anomalies for the 4 missions using a common reference, and also doing handling the sampling errors, doing sampling error corrections as best as we can. So we spend, after this generation of this data record, we spend quite a lot of time trying to understand the actual intermission differences. And this, just by eye here, you can see that, well, low down in the troposphere, there are quite large differences actually, in particular to compare with the earlier missions, of course. But also higher up in the atmosphere, there are some differences, let's say above 40 kilometers. For CHAMP and GRACE, you can clearly see that there are differences due to the low data numbers. And if you compare these taking differences and so on, we can see that there are actually subtle differences between the missions. And this is something that we also, when we develop the data records, we try to understand where these biases between the differences between missions come from and try to address those. Anyway, that was bending angle, low latitudes. If you look at well, go from bending angle to reflectivity to dry temperature and separate into different altitudes, we see here that well, let's see. There it is. So we see that low down here, we can see that there are quite large differences in so let's say between 5, 6, 7, 8 kilometers. There are quite large differences between the missions. There is a region between 8 and 30 kilometers, which we have used a lot in various studies, which is where the differences are quite good actually. They're very consistent. And for bending angle, we could go up to 40 kilometers, reflectivity a bit lower, dry temperature even lower. There we see above 30 kilometers, we see some differences. There are also some differences actually with CHAMP data. So some work needs to be done on that. Okay, so the applications here, this is a number of applications, just a list of applications where we have been involved in. And it's climate reanalysis, atmospheric monitoring of climate time series in general, evaluation of other type of sounders, microwave and IR sounders. That's an important one, and also evaluation of humidity time series. That's actually something that is gaining a lot of interest. So this focus on humidity is clearly important. Equatorial stratosphere, QBO zonal winds, and as we heard previous speaker here, not just zonal winds, but also the whole wind fields in the stratosphere is something that is being worked on. Trends, of course, we have this contribution to the last IPCC report, as Andrea mentioned here. Climate model testing, something that is clearly important and a bit of underexploited also. And there are various applications for the polar stratosphere. At DMI, for example, conditions associated with ozone depletion is very interesting. So trends. We have here, let's see. There it is. So these are trends from, it's not the full time series actually, it's from 2002 to 2020. It's in bending angle, in reflectivity, and in dry temperature. We see here that the largest trends in bending angle and reflectivity is actually in the, it's actually higher up than the largest trends in the temperature. It's in the lower stratosphere. And we see also that if we take a look at how the trends evolve as we take longer and longer time series, it seems that they have, at least at low latitudes, they have actually converged with just 20 years of data. It's at higher, mid and high latitudes, it of course takes longer time, the variability is larger. But at low latitudes, 20 years is enough to overcome this natural variability. And this was quite a long time ago now, in 2008. Mark Ringer and Sean Healy, they did a study based on the climate model, the Met Office climate model at that time, HADGEN-1, where they actually computed bending angle trends to understand how long time it would take for trends to be clearly visible. And this is the trends, the HADGEN-1 model trends that were published in 2008. There is a simulation from 2000 to the early 2020s, and we did a couple of years ago, 2 years ago, we just took our bending angle trends for the same period, computed it, tried to do the same type of plots, same contour levels and so on. And we came up with this. So it's so this was published in 2022, and it's a remarkable similarity. It's probably much of this is probably a coincidence that it's so similar, but it's still fascinating to see how similar trends are compared with what they said in early climate models back in well 15 years ago now. All right, so this is something that should be studied, and this is we have at DMI. It turned out we have 18. There's a one of the researchers had downloaded 18 CMIP6 climate models. So we put a student just a month ago, just picking up one member from one ensemble member from each of the 18 models, compute trends in the same way as we do in the ROMEX data. And you can see here, these are the radio occultation trends here. And then you have the same trends from these 18 models. Where is it? How many models are there? Oh, it's 21 models. Okay. And it's to me it was a surprise to see how much the trends differed between the models. So this variation in trends here actually is both differences between models, but is also differences, random differences between different realizations. Okay, IPCC report, we've seen this before. The conclusion was that there is a great deal of correspondence in large parts of this, but also some differences that needs to be explained. We saw this. So this is a plot that was shown in the IPCC report, where this is our data, and this is actually trends computed from large means of many climate models. I think around 30 climate models went into computing these trends, different scenarios here. So that's why we see different trends. And one thing that is clear, that we don't see this asymmetry in the models as we see in the observations. I'll skip this because I run out of time, I think. This is it's Arctic stratosphere and identification of very cold regions leading to ozone depletion. Anyway, we are trying to develop the CDRs here, of course. There are potential for improvements. We will aim to reduce biases in the middle upper stratosphere. We also will have some sort of focus on improving the stability in the 1D solutions in the troposphere and sort of generate humidity data records of climate quality. Improved error estimation, uncertainty estimation, with the help of Wegener Center, try to implement a consistent uncertainty description across the levels, from the low-level data up to monthly mean gridded data, and also enhancing the gridded data to higher spatial resolutions, specific synoptic times, and things like that to make it more relevant for the climate model community. So the data record currently existing, that's version 1. We have version 2, which we will start reprocessing this year, released in 2025 according to plans. Champ, Grace, Cosmic, and METOP are included in the plans. Other missions may be considered, but no promises there. And we will start the generation of the new METOP interim climate data record. That version will include reduced high altitude biases, the kappa correction, for example, improved orbit determination, which will solve certain problems that we saw in the last version. Tropospheric data, we will have an updated 1D processing, which hopefully will lead to an improved water vapor data record, and we will have more more vertical gridding also to adapt as an adaptation to the climate model community. Then version 3, we have said that it will probably start in 2027, perhaps be released in 2027 or 2028. There will be for sure be more satellite missions included there, Sentinel-6, Cosmic-2, for example, METOB-SG, that is available, possibly others also. We will also work, up to that time, we will also try to work with new 1D-VAR humidity retrievals for climate applications to really have a focus on the long-term, on the stability, long-term stability and the homogeneity. Yes, so conclusions, we have this data record, 23 years by now, high consistency between our missions in certain regions, a little bit lower consistency in other regions. Humidity data, we see some bias shifts here and there, not in the data record, which propagated from the background data. Climate model testing still a bit underexplored. We should think that should have a clear focus. There is a firm commitment from EUMETSAT and ROMSAF to make these climate data record, hopefully next version available next year. And we are looking forward to contribute to the next IPCC report as well. Yes, that's out for me.
Thank you, Hans. This was a very nice talk. I don't think we have time for questions, so I would like to invite the last speaker for this session, Siwei Yu. And the topic of this discussion is insights of